Hi, this is Raphael Mudge, the creator of Cobalt Strike. Welcome to part 4 of Red Team Operations with Cobalt Strike, Weaponization. In this lecture, I'm going to introduce its namesake, Weaponization, and then we're going to talk about methods of weaponization. We're going to talk about how to generate an executable, or DLL, for your Cobalt Strike payload, and how to customize that process. We'll talk about scripted web delivery and Cobalt Strike's resource kit. We'll talk about the built-in user-driven attacks in the Cobalt Strike product. And I will show you how to use a Metasploit framework exploit to spawn a Cobalt Strike beacon. We will also talk a little bit about how to bring custom attacks into the Cobalt Strike product. And we'll close this presentation with a discussion of tradecraft. So, what is weaponization? Weaponization is to combine a payload, like beacon, with an artifact or exploit that will execute it. I want to expand on that definition of weaponization. An artifact is a file, and that could be an executable, a DLL, PowerShell script, something that embeds something that will run our payload or our payload itself. The goal of the artifact is to create space in memory, copy our payload to it, and pass execution to where our payload resides in memory, or the stub that is going to run our payload. Now, in Cobalt Strike's offense model, you kind of have two kinds of artifacts. One type of artifact will embed a very small program called a payload stager. And when I introduced stagers, I stated that their value is that they fit in very size-constrained places. Like, for example, a PowerShell one-liner where the entire script, including your embedded payload or payload stager, needs to fit within the 8,000 characters allowed for a Windows command line program. So it's very possible that your artifact, just because of constraints, has to embed a stager. And what a stager does is, in turn, it reaches out to the internet and it downloads a payload stage. And this is the actual beacon DLL. So it actually downloads the payload stage and passes execution to it at position 0. And one thing that's special about this DLL is that it was modified in the beginning to kick off some code that allows it to bootstrap itself and situate itself in memory and start executing. We're going to go into that process a lot later on. But right now, I just want you to be aware that when you have an artifact that contains a stager, what is shipped with that artifact is, well, the stager, not the payload. And that is beneficial when you are dealing with size constraints. Now, the other option is to skip the stager altogether and to not embed that into your artifact. And instead, to embed the entire payload itself. And we refer to that as a stageless artifact, because your artifact now contains this entire 250 kilobyte blob that is your payload. And mechanically, our stageless artifact does the same thing it would do if it were running a stager. It allocates memory, copies the thing to it, and passes execution to it, and away we go. The first type of artifact I want to concretely talk about are executables and DLLs. You can generate a stageless executable or DLL artifact, and that again is an artifact that embeds your payload without a stager. Go to the attacks packages Windows Executable S for stageless menu in Cobalt Strike. When you export a DLL via this menu, be aware that you have the option to use Rundle32 to kick it off. And to do that, just use Rundle32 to run the exported function startW. When you use Rundle32 in this way, make sure that you generate a DLL that is an architecture match for the Rundle32 you're running. So if you're running a 32-bit Rundle32, use a 32-bit DLL. If you have a 64-bit Rundle32, use a 64-bit DLL. I do want to briefly mention how to host files on Cobalt Strike's web server. You're aware that Cobalt Strike has a web server. It's used for Cobalt Strike's HTTP and HTTPS beacon. You can host files on it as well. Just go to Attacks, Web Drive-By, Host File. If you want to manage or even remove hosted files, go to Attacks, Web Drive-By, Manage. And if you want to see activity directed at your web server, go to View Weblog. One note is that the web server in Cobalt Strike has some, I want to call it circa 2012, protection from curious blue teams, and that is it will return a 404 response when it gets a curl, wget, or links user agent. So if you use any of these to pull down a file, make sure you change the user agent. That's all. Let's generate an executable and host it on Cobalt Strike's web server. Go to Attacks, Packages, Windows Executable S, and press ... to choose the payload to create an executable for. Press Choose. Now for output, we can choose PowerShell, a raw position-independent blob, a Windows exe, a service exe, or a DLL. We're going to do a Windows exe, and we will make that 64-bit. Press Generate, and we will save this as beacon.exe. Great. Now, let's go to Attacks, Web Drive-By, Host File. Press the folder to choose the file you want to host. In this case, we will choose beacon.exe. And now we get to set the URI of where to download the beacon from, or where it's going to be hosted at. So we'll just put something with a lot of slashes in there. I'm just being playful. But press Launch and put that in the clipboard. And here we are on our Windows 10 target. Let's try to download our beacon.exe. Press Run. And snap. We just got snagged by antivirus. And to deal with that, we're going to need to talk about the Artifact Kit. So what is the Artifact Kit? The Artifact Kit is a source code framework to generate executables, DLLs, and service executables that can potentially bypass some types of antivirus technologies. The Artifact Kit builds on a contract that is available via Cobalt Strike's aggressor script. When Cobalt Strike generates an executable or DLL, it asks its scripting engine, says scripting engine, can you generate this executable or DLL for me? And if a loaded script says yes, Cobalt Strike says, okay, well, here's my shellcode. Give me that executable or DLL. And the script turns that over, and Cobalt Strike uses that instead of what's built in. That mechanism, you can build whatever you want on top of it, so long as it works. The Artifact Kit is just an example of something that builds on top of that mechanism. So to download the Artifact Kit, just go to Help, Arsenal, and you will have the ability to download the Artifact Kit. To benefit from the artifact kit, it really helps to understand how endpoint security products look at executables and DLLs before they are run. And this pre-run caveat is very important because there are certainly detection events and opportunities after an artifact is run. And we'll talk about those when we get to tradecraft. But for now, I want to go through the gymnastics a product uses to determine, is your executable good, known good? Is it bad? Or is it something that is inconclusive or unknown? And what happens in these cases is going to be very dependent on the product and how it's configured. Naturally, if your executable is determined to be good, it's going to be allowed to run. And if your executable is determined to be bad, it's not going to be allowed to run, and there's going to be an alert that's raised. Those outcomes make sense, right? Well, what happens in the case of unknown? And again, that is dependent on the configuration of the product. In some cases, unknown is a default where it's just treated as good and allowed to run. In other cases, unknown is an opportunity to raise a scary prompt and to really warn the user and say, hey, I don't know, are you sure you want to allow this to run? So that's another aspect. But unknown is also an opportunity to escalate the detection response effort to the cloud and to pass the binary and meta information about it back to the vendor and to see if after the escalation a determination can be made that it's bad and we need to alert. A determination can be made that, yep, this is good and should be allowed to run. Or we end up in the same inconclusive place and the user gets a scary prompt. When it comes to the topic of local analysis, the things that are done to determine known good, known bad, or inconclusive, there's really two approaches you have to worry about. You have to worry about static analysis, where your content is looked at as is to determine which you are. And you have to worry about dynamic analysis. Let's go through these. Let's start with static analysis. What are the strategies for static analysis? Well, one is rule-based. And this is looking for content in the binary file that match analyst definitions of known bad. Another are heuristics. And heuristics are a way of looking at observable properties of the binary to find things that are suspicious, and enough suspicious things may put us over the edge to determine, hey, this is potentially known bad. What are examples of some heuristics? Well, the compile time of the binary could be used to determine how new it is. The suspected compiler could be used as a heuristic of, how often is this malware versus a valid third-party program? A good example is Windows Defender seems to really consider anything not compiled with Visual Studio to be suspicious or to be given a bump up. The import table is another example of something that can really trigger some certain kinds of heuristics. Looking at the import table, you can make a determination of what you think the program might be doing. Is it going to be popping up windows on a desktop and doing stuff? You might see that in the import table. Is it making a network connection, spawning a program, injecting shellcode into it? You might see functions that kind of help indicate that in the import table. So the import table can be a rich source of information to signal intent. Also, metadata and resources within the application. And metadata are things such as what is the name of the application, what is its icon, or even the absence of this information can indicate something that is different than a program a normal user is going to run. Whether or not the program is signed by a code signing cert, that can be something a heuristic looks at. And entropy is another item. Let's say you've got your known bad embedded into a program. You don't want it to be immediately visible, so instead you obfuscate it or encrypt it. Well, this might show up when looking at the entropy of the section of your binary that has strings, because it might look like there's a lot more random data there than normal, and because of that, a heuristic analysis might conclude, there's packed data in this application. So really the list here goes on and on and on, but these are features, observable things about a program that could lead one to score whether or not they think the intent is malicious or benign. The last one I want to speak to is what I'm calling correlation. And correlation is kind of interesting. Let's say we've got our binary right here. What you do for this particular aspect of one approach is to look at this binary and generate a list of numbers, or you could call it a vector, that summarize what we know about the binary. And the vector can be things that would show up in a heuristic, but they can also be things like unique sequences of bytes to kind of get a unique fingerprint on some of the content in this file. When you have this vector, what you can do is compare it to a library of vectors shipped with the antivirus product. And that library might include known good programs and known bad. And you can use well-known tools, such as Pearson's correlation coefficient, to compare your vector derived from the executable or DLL being analyzed to this library to determine which of these vectors you're most like and to what extent you correlate. And these two values can give you an idea of whether or not the observed binary is known good with a reasonable or not confidence, or whether or not it's known bad, and again with what degree of confidence. And that's basically how some of these machine learning or statistics approaches work. When you hear a vendor describing a signature as resilient, this is likely what they're talking about is a correlation approach to map what they're seeing to previously observed known good or known bad. So how do you push back on this stuff? Well, with rule-based signatures, you can obfuscate your bad content or whatever you think is bad, such as your shellcode or payload, or just change it until you break what you understand is the signature. Or if you know the signature, try to work within what it allows, but don't be what the signature triggers. For heuristics, you can take on metadata from an existing program. And there are different programs out there to clone metadata and resources from other programs and transfer them to a binary. For heuristics, I also recommend doing things like paying close attention to your import table and don't let it signal the offense intent of your program. So if you're going to do things like shellcode injection into a remote process, make sure that you consider dynamically resolving the needed functions with get proc address and get module handle instead of populating your import table with that stuff. And consider signing your code as well. So use a valid code signing cert, sign your program. For correlation, the approaches that help with 1 and 2 are certainly going to help with making it harder to correlate with something that is known bad or previously associated with your current tool set, like Cobalt Strike. But let me give you an idea of like where correlation goes as well. So here's a binary. And earlier this year, researchers demonstrated that they were able to take a binary that was known bad, an unaltered known bad example, and append to it a program that was known good. And this program, this particular endpoint security product, happens to use that correlation approach I spoke of. And it just turned out that the score, the vector that the new binary overwhelmingly correlated with, was the known good. And therefore, this particular endpoint security solution let the binary through. So it is possible to mess with these kind of machine learning statistics-based approaches as well. Let's talk about dynamic analysis. So far, our binary has passed a static check. So we don't have any known bad inside. There's not really enough going on here for a heuristic to make a good choice. And our binary and its characteristics don't correlate with anything in that product's library of known bad or known good. Embedded within this program is our obfuscated known bad. So the reds are known bad, and the blue just happens to represent the layer of obfuscation I've applied to it. All right? So what does an antivirus product do to defeat this kind of evasion? Well, this is that light form of dynamic analysis I mentioned called sandbox analysis. So some AV products have a very simple CPU emulator. And that emulator will have data structures that capture changes made to memory in this emulated CPU, and maybe even to the file system or other parts of the computer. And what the product does is it starts at the entry point of our binary and starts executing in this virtual sandbox each instruction in our program one step at a time. And when we hit an API call, of course, we emulate that API call and resume execution. And the goal of this technology is that eventually, in stepping through the binary, our known bad will show up in this emulated memory. Okay? And as our known bad shows up, as we keep stepping through and emulating, possibly more and more of our known bad becomes deobfuscated to the point where, voila, we see our known bad, either content or maybe even a sequence of behaviors that indicate, certainly something we don't want to allow is happening here. So we get to the point in our emulation where we've detected something and made a determination that indeed this binary is known bad. So that's that light sandboxing emulation, that light form of dynamic analysis. And you may say, that's interesting. Okay. What can I do to push back on that? Well, this dynamic analysis has two constraints, really, that are very important. The first is time. It can only step through and emulate the binary for so long before it's got to take what it has and make a decision. The second is incomplete emulation. It's very possible that this sandbox is not able to emulate everything that your program could do, or it may emulate it in a way that is wrong and you can use to your advantage. So, for example, let's say we do know over here is our detection point, right? This right here, and we never want to get here. Well, in our binary, we could have a sequence of instructions. Obviously some things are going to get emulated just fine, so they're getting emulated, but we could have an API that the sandbox doesn't know what to do with. And in that case, the sandbox might have to give up and stop emulation. And if it does, the endpoint security product has to make a determination based on what it knows. Or we could use the incomplete emulation and inaccurate answer to drive a branch where a program starts doing something else that never actually reveals or gets to executing our malicious behavior or doing something that is expected to be bad. So that's an example or examples of taking advantage of this incomplete emulation. The time thing, you may have heard of approaches such as encrypting the shellcode and working to brute force the key and having a very weak key, but something that still mathematically takes 10 to 30 seconds or whatever it is to brute force. And that's an example of an approach based on time to defeat this kind of analysis. And all of that was the lead up to explain how does the artifact kit work? How does the source code framework help us defeat some kinds of executable and DLL detection strategies in endpoint security products? Well, the idea behind the artifact kit is to obfuscate known bad into an unknown executable. Making Cobalt Strike's executables unknown is definitely an exercise that is in your hands. But the artifact kit does try to take different approaches to fool the AV sandbox to stop emulating the executable. And that is to defeat that dynamic analysis step we talked about. Once that's done, the artifact kit executables deobfuscate our known bad and pass execution to it. To download the artifact kit, just go to Help, Arsenal, and Cobalt Strike, and that will take you to a page where you need to enter your license key, and then you can download the artifact kit. I recommend that you modify or obfuscate it as necessary, build it, and then load a script to use your artifact kit. Let me give you a lay of the land of the artifact kit real quick. So the artifact kit is built with the minimalist new for Windows 32 on Linux. And this is a compiler toolchain with headers and libraries needed to build Windows EXEs from Linux. I mentioned that your compiler can be a concern to some heuristics. And this one is not the compiler that's in your favor. You really want to use Visual Studio if you can. But for building new executable and DLL templates from your operating platform, this option can't be beat. It's really, really nice. So that's why the artifact kit uses that. And the script to build new artifacts is build.sh. Let me give you an idea of the layout of the artifact kit and how to navigate it. So we've got two folders that really matter to us. It's source main and source common. And within source main, we happen to have C files that are the entry point to our different artifacts. So main.c is just plain executables, service main.c are service executables, and DLL main.c are for our DLLs. Okay? And that's kind of step one of the artifact kit, and what it's doing is these are your entry point for your artifacts. The next one we have for each artifact kit option is we happen to have a C file that is bypass something.c. And what this is responsible for is taking steps to defeat the dynamic analysis. So this is where your AV sandbox bypass steps come into play, is in this particular file. And so there's a few different strategies that are in the artifact kit. The next step taken by every single artifact lives inside of patch.c. And what patch.c does is it deobfuscates our embedded payload or payload stager and gets ready to execute it. So that's what patch.c does. And in the simplest case, this is where the artifact kit ends, because usually executing it will be just creating a thread or doing something else. But some artifacts do migrate. And to do that, they spawn a new program, which is rundle32.exe by default, and you probably don't want that. These artifacts then allocate memory in that temporary process and create or hijack a thread to run our payload in that child process. And so injector.c and startthread.c control this process. And so that's our kind of fourth step, which is optional for some artifacts, and that's migrating. And there you have it. That's the artifact kit. Let's take a look at the artifact kit in action. Go to Help, Arsenal, and you can download the artifact kit with your license key from this customer-only download page. Here we are in my home folder, and I'm going to extract the artifact kit, which I had downloaded previously. Here you can see we have our source main folder with that step 1, the entry point to our different artifacts. We have source common, which has the different bypass options to defeat the sandbox emulation. And we've got our code that is associated with deobfuscating our payload or stager and passing execution to it. And we have injector.c and startthread.c, which are associated with migration when the artifact does that. So that's the layout. We do have build.sh as well. If you want to extend the artifact kit with a new option, you can. Just copy this build artifacts line and create a new artifact kit option based on the bypass you have. So for example, bypass new, you might have something dist new and go from there. And in a similar way, you would do that for the 64-bit artifacts as well. And in this way, you can create a new bypass option. So that's a little bit on extending the artifact kit. Today, we're just going to work with the dist pipe option, which is the default in Cobalt Strike. So I'm commenting out these others to allow our build process to go faster. Let's go ahead and jump over to bypass pipe and explain its strategy for defeating sandboxing. So let's go to source common and open bypasspipe.c. And the strategy of this particular bypass is to create a name pipe client and server and to pass our obfuscated payload or stager through it. The theory being some antivirus sandboxes, especially circa 2014 when this was made, will not emulate name pipe communication properly. So that's the dist pipe option. Let's just go ahead and rebuild it and get back a new compiled set of binaries. One thing that's valuable about rebuilding is your compiler, even if it is the same one, the minimal new for Windows compiler chain, even if you're using the same thing, you probably have a different version than I do, and that might make your binaries look sufficient enough to give you some advantage. So we've recompiled the dist pipe option. Let's go ahead and load it into Cobalt Strike. Go to Cobalt Strike, Script Manager, press Load, go to Artifact, Dist Pipe, Artifact.cna. This script registers itself with Cobalt Strike and says, hey, Cobalt Strike, if you need an executable or DLL, talk to me. I have it. And let me show you what that looks like. Let's go up to dist pipe. And let's open up artifact.cna. And this line here is how the script registers itself with Cobalt Strike. And whenever Cobalt Strike wants a certain kind of artifact, and it will give the name, this script has a chance to generate that based on its own templates and embed the passed-in payload or payload stager into it. So again, Artifact Kit is an implementation, a source code framework that takes advantage of this hook, but you don't have to use Artifact Kit. You could build something else on top of this. All right, so we've loaded our Artifact Kit script. Let's create a new executable. Attacks, packages, Windows executable S, ... choose our beacon, 64, press generate. We will save it as beacon.exe. Press OK. Go to attacks, web drive by, host file, grab it out of this folder, and look for beacon.exe in our root folder. And we will call it testa.exe. Press launch, copy that to the clipboard, and let's come over to our Windows 10 target. Let's paste that in, press run, and as we might expect, because we didn't change anything, we get snagged by antivirus. Let's come back to Kali Linux and let's go to work. All right, here we are back in our Cobalt Strike instance, and we're going to apply a couple of the strategies we talked about in the whiteboarding session a few moments ago. So I'm going to open up a tab, and I'm going to run strings on beacon.exe. And I want to show you a few things. Here we have the import table, and we have several strings that were generated by our compiler and several strings that are part of the functions that got linked into our runtime or our executable to make everything we want to do work. And there's also some meaningless strings that are probably there just by coincidence. But one string that does pop out as being unique to this binary and possibly a good signature point is this one right here. And that is actually our named pipe name. So we're going to change that, and we're going to muck around with our import table a little bit to get rid of things that might indicate we're taking steps to run shellcode. So let's jump over to artifact, source common, and let's open up bypasspipe.c, and we're going to go to the bottom of the file, and we're going to change this string where we are trying to obfuscate our pipe name, but ending up with a string that's pretty obvious anyways. So we're going to change that to pipe. We'll put in a backslash there, and that looks okay to me. And again, the point is just change it. All right. The next thing I want to do is I want to mess around with the code that we use to deobfuscate our payload and pass execution to it. And that process happens in patch.c, patch.h. So let's come down here, and we have our spawn function. And this is doing a very classic pattern. It's allocating memory, changing the permissions after we allocate it, and in this case, we're calling create thread. Let's get our executable memory a different way than using virtual alloc. And to do that, we're going to jump over to our very friendly Microsoft Windows documentation, and we're going to look up a function called heapalloc. And heapalloc is a way to allocate memory on the heap. And to allocate memory on the heap, we do need a handle from heap create that is actually configured to create RWX memory in our heap. So we're going to do a little bit of programming here, but not too much. We're going to create a variable. Will be lp void heap, you would think I would be able to not do typos. And let's say create our heap. We're going to do heap create, and we need some arguments. So let's do as our options, heap create enable execute. And then for the initial and maximum size, I think zeros will do what we need. So yeah, if we're a 0 for the maximum size, the heap should be able to grow as much as possible if we set that to 0. So let's do that, 0, 0. Now, instead of virtual alloc, we will use heap alloc to allocate memory on our heap that we just created. And the arguments here are the heap, any flags, and the length or size. And I don't think we care about these options, so let's do heap alloc. And we will do the heap, the flags, and the length. We'll get rid of virtual alloc, get rid of virtual protect. And now we have a spawn function that largely does the same thing, but is coded a little bit different, uses different Windows APIs. Let's come over here, run build.sh, and what do you know? I made a mistake apparently, didn't I? Let's press Control-C, and let's fix my syntax error in bypass pipe.c. And I must have stepped on one of my %C's when doing the pipe change here. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. I'm making sure that the number of arguments here match here, because originally this was my way of trying to obfuscate this, which was back pipe, back whack doc, whatever our pipe name was. So that's what's going on right there. Just obfuscating our embedded pipe in the binary. All right, this looks okay to me for the moment. Let's try building again. And looks like things are going a little bit better. Good. So now we just have to wait for our artifact kit to rebuild. One thing to note, we don't need to reload the script because the script didn't change, just the template. So we can go ahead and change things and try this out as is. All right, let's go over to Cobalt Strike, go to Tax, Packages, Windows Executable S, choose our HTTP beacon, 64-bit, generate, we will call it beacon2.exe, press save. Let's host it on our Cobalt Strike web server, tax web drive-by, host file. We will choose our beacon2.exe, and we will call this test2.exe. Press launch. Oh, .exe, not .txt. Now, press launch. Copy it to our clipboard. And here we are back in our Windows 10 system. Let's grab test2, run. We get back a scary prompt. And this isn't a AV hit. This is just, I don't know what the application is. And this might mean that, okay, great, we can't use this executable as is in a fish, but this executable might be suitable for persistence or lateral movement. And that's why I'm not that worried about Smart Screen. But having executables that you can use are very important. Here we are back in Kali Linux, and we can see that we have a foothold on Workstation 1 in our test2.exe file. So that's an example of using the artifact kit to defeat a static signature and local sandbox analysis. I want to close out our discussion of executable and DLL analysis pre-run by talking about the cloud strategies. We already discussed the local parts of the analysis. We talked about the static analysis and the light dynamic analysis. When this process is inconclusive, some products, depending on their configuration, will escalate the analysis to the cloud components in the product. And the first phase of this is usually a metadata analysis. And when analyzing metadata, there's kind of two opportunities here. First, the SHA-256 hash, or some hash of the binary, may get sent back to the vendor cloud, and that's an opportunity to reference any previous analysis and any previous verdict related to the binary. And it's also an opportunity to look at its uniqueness. If you're seeing a wave of unique executables showing up in a customer's environment, that can be an indicator that this deserves a further look. So that's an aspect of the metadata analysis piece. Now you may recall that during the static analysis whiteboarding session, I was talking about this idea of taking a binary and deriving a mathematical fingerprint or a vector that summarizes different observable characteristics of the program. Okay? And one way of having resilient signatures is to compare this vector to a library of vectors derived from similar kinds of binaries or from just other executables and DLLs. And that library can consist of known good and known bad. Now locally, this kind of analysis has its limitations. The more vectors you want to compare against, the longer it'll take. And there is certainly a CPU constraint here. But by escalating this analysis to the cloud, you can use a much, much bigger library of things to try to compare or try to find a correlation between this candidate executable or DLL's vector and something else. And this is how a cloud program or a cloud component to an endpoint security product can come up with a detection when the local product failed. It's because it's dealing with a much, much larger library of things to compare against. And as an offense operator, the strategies for dealing with this state of affairs are still the same as what we talked about for dealing with static analysis in general, which is try not to look like known bad or a known offense tool set, and try to take on the characteristics of known good as much as possible. The next escalation is to detonate the binary in a sandbox. And that's where the executable or DLL is uploaded to the vendor's servers, and they run the DLL in a full-fledged, heavily instrumented virtual machine. And here you run into situations where you've got your program is running, and of course, maybe we masked our known bad, but when our program is running and being emulated, our known bad comes up visible clear as day. And a heavily instrumented VM can provide a lot of insights into the program, a lot of opportunities to figure out what it is. And its memory content is certainly one aspect of that, its network traffic, its behaviors, etc. If you've ever seen a connection to your Cobalt Strike from something like Joe PC, and the user is Joe running in a high integrity context, you didn't hit the phishing jackpot. Your binary is being detonated in a sandbox or virtual environment. So what are the strategies to deal with this kind of analysis? Well, really, there's kind of two sides to the same coin here. The first is try to detect the sandbox And if you detect that you're running in a sandbox environment, do something benign, but don't go so far as to take the steps to reveal your offense functionality. The other side of the same coin is, instead of detecting the sandbox, try to detect when you're running in your target's environment. And this is environmental keying, where you're looking at either the context factors of your environment or steps you took to prepare the environment or binary, such as setting an environment variable or even a command line argument, to make it so that when your program is detonated, if that context is missing, your offense functionality is not revealed, and instead something benign happens. So broadly, those are the strategies for dealing with these cloud components. And if you get stuck on this for whatever reason, consider treating this like the application whitelisting problem. And that's a good segue to talk about application whitelisting. Application whitelisting are different technology implementations that aim to prevent the execution of unapproved applications. The idea is only things that are in a certain whitelist are allowed to run. The strategy here is to run your payload via a whitelisted program. For example, if you're worried about your initial phishing vector, a Microsoft Office macro may be attractive because Visual Basic for Applications can call the Win32 API. PowerShell is attractive and has been abused heavily for similar reasons. Now let's say that the application whitelisting technology is a very, very broad whitelist. For example, the technology may have a setting that says, hey, we're going to allow anything that is a Microsoft signed binary to run. Well, if that's the case, then you get into the realm of LOL bins, or living off the land binaries. And these are programs both shipped with Windows or even available for download elsewhere that are signed by a trusted party like Microsoft and have functionality that allow you to run a payload in the context of that trusted program. Another strategy is to take advantage of DLL sideloading. Again, this is application whitelisting technology dependent, but in some cases, a program will search user-writable folders for DLLs that it needs to load. And so if you have a whitelisted program that does this, you can drop a DLL that will run your payload to this user-writable folder and use this trusted program, this whitelisted program, to load your payload into its process space, getting you around application whitelisting. The DLL sideloading strategy is dependent on an application whitelisting solution that does not restrict DLL loads. Another weaponization tool is scripted web delivery. And we've already seen multiple demos of scripted web delivery in this course. Go to Attacks, Web Drive-By, Scripted Web Delivery. This feature will generate an artifact, host it on Cobalt Strike's web server, and give back a one-liner to download and run that artifact on a target. Scripted web delivery is not very interesting from an evasive point of view, but that's not its point. Scripted web delivery is a very valuable tool to create a foothold when doing an assumed breach engagement. When you use scripted web delivery in Cobalt Strike, I would fully expect that the built-in script template for PowerShell or whatever will get snagged by the antivirus product solution in place. Similar to how you can change Cobalt Strike's executables and DLLs with the artifact kit, you can change Cobalt Strike's script templates that run payloads with the resource kit. Let's take a look at the resource kit. Go to Help, Arsenal to download the resource kit. On my virtual machine, I've already downloaded the resource kit, so we're going to extract it And if we go to the resource kit folder, here are the script templates that Cobalt Strike uses to run a payload in its post-exploitation and user-driven attack workflows. If we look at resources.cna, this is the script that registers itself with Cobalt Strike and says Cobalt Strike. If you want a script to run a payload, let me give you that script. You just tell me the file you want and give me the shellcode. I will do the rest. For example, if a piece of automation needs the 32-bit PowerShell template, here the resource generator says, okay, well, let me take the file that we read in, which was template x86 ps1, and let me XOR mask the payload or payload stager with the key 35, the byte 35, and let me base64 encode the whole thing. And then let me patch that into the template by replacing %data% with our transformed script content. And conversely, if we open up template x86 ps1, you will see that it is being extracted by base64 decoding it, and that masking step with the XOR operation is being undone. So that is how a PowerShell script is transformed. In a moment, you're also going to see that some PowerShell scripts are sometimes compressed, and the steps to do that are controlled here as well. When Cobalt Strike wants to compress a PowerShell script, it gzips it, base64 encodes it, and patches it into the decompressor script called compress.ps1. And that looks like this. Nothing too crazy. Let's come over to Cobalt Strike and let's go to attacks, web drive-by, scripted web delivery S. And let's host our script at something like /zz. We'll make a hosted script for our HTTP payload. We'll stay 32-bit, hit launch. Let's copy this to the clipboard, and here we are on Windows 10. For this demo, we're going to use PowerShell ISE. When I'm playing around with a static script template, especially a PowerShell one, I really like to work with this tool. By the way, if this is what you see by default, click the little down arrow to show the script pane. All right, let's do this. Let's grab our download cradle as is, press run script, and sad face. We are blocked by our antivirus software. What can we do next? Well, ultimately, we want to change the script in some way to break the static signature. And how you figure out where that is up to you, but let's walk through this front to back. So let's replace IEX with setClipboard-value, and let's do our download string line again to get the other stuff into the clipboard. Paste that in, and you can see this is our compress.ps1 populated with a base64 encoded gzipped script, right? Let's press run script, and go figure, this is blocked by AV. All right, no surprise. Let's unwrap this a little bit and see if the inner layer is where the detection is. So let's change IEX to be setClipboard-value. Press run script. And now we've got the script in our clipboard. Control V to paste it in. And let's see if this is what's detected. Press run script. And yes, it is. This is still being blocked. All right, fine. Let's go through and comment some stuff out. And let's see if we hit run script, if that makes a material difference. Interesting. No detection. All right. Well, let's start uncommenting one line at a time. Do run script. and see if we can reintroduce the detection lines. So let's uncomment that line, run script. Let's uncomment this line, run script, and snap. We're getting detected. All right, well, let's make some changes. Me personally, I like subtlety, so it doesn't really matter, but let's do this. Let's try changing it to copy. All uppercase, run script, same thing. Okay, fine, you don't like my copy change. Let's change 0 here to 0 by 0. They mean the same thing. Run script. Interesting. Seems to work. Let's come down here and uncomment these last 2 lines, hit the run script button, and it looks like we're running. Here we are back in Kali Linux, and no kidding, we have a payload. All right, let's make a change to our resource kit template and try this out end to end and see if it makes a difference. So let's come over to our terminal. Let's open template x86 PS1. And let's change that 0 to 0x0. And let's make Cobalt Strike use this template. So let's come over to Cobalt Strike Script Manager, load, resource kit, resources.cna. And now that this script is loaded, Cobalt Strike will use those templates. Let's go to attacks, web drive-by, scripted web delivery. We'll do /mm, listener, choose launch. And let's try running this. But before we do that, right-click, session, color. We'll mark this one just so we know that we've already seen it. And here we are. Let's go start, run, paste in the one-liner. Back to Cobalt Strike. And there we go. We now have our new session. So that is a demonstration of defeating a static PowerShell signature using the flexibility given to you by the resource kit. Cobalt Strike does have several built-in user-driven attacks. You can export an HTML application that runs the beacon payload, a Java signed applet, a Microsoft Office document macro, or even an executable that runs your payload and drops a file to disk and opens that file. You can access these features by going to Attacks Packages or Attacks Web Drive-By. Be aware that each of these options use stagers. Another thing I would like to point out is that user-driven attacks are not a core focus of the Cobalt Strike product anymore. These are very much a legacy capability. You do have the flexibility to change the implementation of these attacks in Cobalt Strike. Some of them you can modify with the resource kit, you can modify the dropper with the artifact kit, and in the case of the Java signed applet, you can sign it and modify it with the applet kit. Let's say there's a really cool module in the Metasploit framework, and you would like to use that to deliver Cobalt Strike's beacon payload. Well, here's how you use the Metasploit framework to run a 32-bit beacon. First, pick an exploit that you would like to use. Second, set payload to Windows Meterpreter reverse HTTP for an HTTP beacon, or Windows Meterpreter reverse HTTPS for an HTTPS beacon. Set lhost and lport to point to your beacon listener, and set disable payload handler to true. If the exploit module is memory corruption on an application and you want to migrate for stability reasons, set prepend migrate to true. Once the module is configured, run it with exploit-j. The reason all of this works is because Cobalt Strike is compatible with the Metasploit framework's staging protocol. That said, when you use this process, you are definitely using Metasploit Framework stagers, so be aware of that. Let's take a look at using a Metasploit Framework module to run the beacon payload. Let's click this cute headphones, and we have a HTTP beacon 10.0.0.204 on port 80. Great. Let's open up the MSF console and give that a moment. And we are going to use a type of module called an evasion module. And these were added, I want to say about 2 years ago, or DerbyCon 2018 is when they were introduced. And there's sometimes something really cool here for like defeating whitelisting or whatever. So we're going to use Windows Defender JS HTA. And let's configure this. Let's do set payload, Windows Meterpreter, reverse HTTP, set lhost to our 10.0.0.204, which is our beacon listener. And we're going to set disable payload handler to true. And I don't think we need to migrate here. Let's look at everything. This all looks okay to me. Let's do exploit-j. And it's telling us that this HTA file is stored in root msf4 whatever.hta. Cool. Let's grab it. Right click, copy. In Cobalt Strike, let's go to attacks, web drive-by, host file. And we will, let's navigate to that folder. Let's just go to .msf4, local, and there it is. And let's call this evilmsf.hta. Hit launch. And let's run this on our target. Here we are on our Windows 10 target. I did disable AV. I just want to demonstrate using a Metasploit module to run a beacon payload. Here we are back in Cobalt Strike. And you can see we have a 32-bit beacon running in this random looking process.exe. So that is an example of using a Metasploit module to spawn a beacon session. The final weaponization option I want to touch on is your option to go custom. You can export a ready-to-run position-independent blob with a beacon payload. Go to Attacks, Packages, Windows EXE S. Or, if you want a stager, go to Attacks, Packages, Payload Generator. Both of these have the option to export a raw artifact. Use that with a third-party artifact or tool. And if you have your own clever idea, consider building a script to integrate it into Cobalt Strike. Let's talk about tradecraft. Here's where we're at in our attack chain. Our goal is code execution. Let's dig into that code execution attack chain. The first part of the code execution attack chain is your artifact. This is the executable or script file that runs your payload. And we already talked about strategies for PowerShell and executables to defeat different kinds of static and dynamic analysis. Certainly, smuggling your artifact past an endpoint security solution is part of the puzzle, but definitely not all of it. Once your artifact is running, what can get you is its behavior. Let's say we have a Microsoft Office macro, and that macro happens to run a temporary process and inject our payload or payload stager into it. These behaviors are detection opportunities. Specifically, the process launch is a detection opportunity, and so is the process injection. Another common detection opportunity is writing a file to disk as well. So be aware that the behavior of your artifact, the steps it carries out to get your payload into memory, are detection opportunities. And when you're crafting a code execution strategy, this is something you have to think about and consider. Even with the behavior piece sorted, you are now a injected DLL. And this itself presents some detection opportunities. The content of your DLL in memory is potentially vulnerable to a point-in-time analysis where the content of memory is analyzed looking for you. And the properties of the memory and thread that you occupy can also be used to find you in memory. The last part of this attack chain is process context. And process context works for you and against you because it's often a bound on these other kinds of post-execution detection strategies. Your process context dictates what is allowable behavior. For example, if you live in a process context that normally makes connections out to the internet, you might get a free pass beaconing out over HTTP from that process context. Your process context also determines detection threshold. Some processes are heavily abused or some process contexts and therefore subject to more aggressive detection heuristics than other process contexts. In practice, you'll see this with memory-injected DLLs. If you live in a PowerShell exe context, I would expect to see more aggressive in-memory detections applied to you there than in other process contexts. Similarly, if you are in a highly abused process context, such as Rundle 32, I would expect certain kinds of behaviors to get flagged more aggressively from that context than others. And be aware, your process context is not just your current process. Your process context consists of your parent and child process. And an odd parent-child process pair may get more scrutiny than a normally observed parent-child process pair. And be aware that this information is often aggregated to a SOC to look for anomalous activity happening on targets in their environment. This slide summarizes what we just talked about. Your artifact, its behavior, your payload content and properties in memory, and the process context around all of this affects whether or not your code execution will turn into detection or a safe process context to start post-exploitation from. Here's my advice on evasion. If you are worried about your artifact, test it out with the endpoint security solution you expect to see and obfuscate it. For these behaviors, avoid them if you can. If you can't, adjust them to look plausible. For example, if you are going to execute a program as part of an initial access artifact, consider spoofing the parent PID to have a plausible parent-child process pair. If you are going to do process injection into a new or existing process, test it out with the solution you expect to see and modify it if you need to not get detected. For payload content, we are going to talk about in-memory evasion in just a moment. For process context, do not inject into explorer.exe. If you are in PowerShell.exe, do not stay there. You do not want to be in, and you do not want to stay in PowerShell.exe. Both of these contexts get a lot more scrutiny and have a lower detection threshold in some products than other process context. Do not use Rundle32, Notepad, or servicehost.exe as temporary processes or a place for your payload to reside. These three processes are commonly abused defaults in various offense toolkits. If your initial access artifact is associated with a commonly abused application, for example, you are in a Microsoft Office application, you are in Internet Explorer, or mshta.exe, be aware that your behaviors, your write, execute, or inject, will get higher scrutiny from these contexts, and you will need to adjust. Also, pay attention to your architecture. If you are in a 32-bit context on a 64-bit system, or are running 32-bit variants of things on a 64-bit system, expect more scrutiny. You stand out more. Let's talk about in-memory detections and evasion. In-memory detections are the use of process, memory, and thread indicators to detect memory-injected DLLs. Here are the common in-memory detection strategies. One strategy is to look for a thread start address that is not associated with a memory mapped file. In most programs, any executable region of code is going to be a memory region that is also a memory mapped file. This is because the program itself is loaded as a memory mapped file, and the DLLs it loads are memory mapped files. Memory injected DLLs are usually not memory mapped files, and so if a thread is created without any extra care, it will stand out for this purpose. Memory permissions are another useful property to find memory injected DLLs. Each region of memory has an initial state and a current state of its memory permissions. Both are observable. Read, write, execute permissions are a common pattern in offense tools and something used to find offense tools when using in-memory techniques for hunting. Do be aware that sometimes any region of memory with execute permissions not associated with a memory mapped file is subject to more scrutiny. Finally, the content of the memory can also be used for detection. Generically, some products and analysts look for signs of a PE file in memory that are not associated with a memory mapped file, and strings associated with a tool set like Cobalt Strike or common techniques such as reflective loading. To push back on memory detection strategies, Cobalt Strike has malleable PE. This was introduced in Cobalt Strike 3.7, and it extends malleable C2 to modify beacons DLL. Things you can do with malleable PE include binary padding. You can prepend and append data to your beacon DLL in memory. You can replace strings. You can embed arbitrary strings if you want to create breadcrumbs for an analyst to follow. You can edit certain PE header fields. And you can set hints in the PE loader to enable different obfuscations. Here's an example of a malleable PE block. The block is called stage. Here are some of the options you can set. And the transform x86 and transform x64 blocks are where you do binary padding and string replacement within the beacon DLL. Let's dig into in-memory evasions. The thread start address depends on the artifact or process injection routine that ran the beacon payload. I will share some tips in a moment on how to have a good thread start address. For your memory permissions, avoid artifacts that use RWX permissions. Avoid stagers. The Metasploit framework stagers in Cobalt Strike always allocate RWX memory for the downloaded payload stage. Set Use RWX in your stage block to false. This will make it so Beacon does not use RWX permissions. One really cool option for memory permissions is module stomping. And this does require some explanation. Normally, your Beacon reflective loader package is running somewhere in memory, and its first task is to allocate new memory for the final Beacon DLL to live in. It then copies that Beacon DLL over to that memory, and the permissions of this memory are going to depend on the use RWX flag. Maybe it will be read, write, execute for everything, or a mix of read, write, and read, execute, depending on the purpose of each section of our DLL, of our Beacon DLL. Module stomping is an alternative to this. When we do module stomping, instead of allocating new memory, what Beacon's loader does is it loads the configured module stomping DLL into the current process. It then looks for an exported function to find the middle of the DLL, and it copies our Beacon DLL into that space. And this is called module stomping because we are taking an existing module and overwriting its memory. And in this way, we end up living in a context where our permissions, our initial permissions anyways, are consistent with that of a memory-mapped DLL. We also have the benefit of living in executable memory, or having executable memory, that is now associated with a memory mapped file or a module on disk. So that's the benefit and beauty of module stomping. To enable module stomping, just set the module x86 or module x64 options in your stage block to the desired DLL. I want to caution you, module stomping is a footgun. If you choose a module that one of your process contexts needs to load later, and it instead references your stomped module, it will crash. Module stomping has some protection. For example, if the stomped module is already present when your Beacon is loading, Beacon will resort to the old behavior of calling virtual alloc. The other risk with module stomping is that you choose a stomped module that is too small. If you do this, your Beacon will crash when it's trying to write itself in to that module's memory space. So keep that in mind as well. The other problem with module stomping is you now have this very odd DLL that's not used in many places being loaded everywhere your Beacon is being loaded. For this reason, I would not use module stomping in my daily driver post-exploitation payload. Instead, I would consider using module stomping on a team server dedicated to long-haul access or for your persistent Beacon payloads. This step will make your beacons a little bit harder to find in memory and is a good practice to separate your persistence callbacks from your post-exploitation ones. What about memory content? Here is my advice to change up Beacon's memory content. Consider setting the image size x86 and image size x64 values. These will change the size of image header, which will influence how much memory Beacon requests for itself. I have heard some people say that the fixed size of Beacon in memory is an indicator. Consider using prepend to offset your Beacon payload from that natural boundary, which is the beginning of a page or even the beginning of a region of memory. There is an option in Cobalt Strike called Obfuscate that will take some basic steps to obfuscate the beacon DLL content. I also recommend that you set cleanup to true. Cleanup will have beacon clean up its reflective DLL package once it's loaded. If there is a troublesome string, something that is being used in a Yarrow rule, try using string replace or string rep to edit out that troublesome string. Another cool option is sleep mask. When this is enabled, beacon will obfuscate its code before it goes to sleep. And when the agent wakes up, it will deobfuscate its code. So if something is getting you that is in the beacon DLL itself, sleep mask is a great way to deal with that. I want to walk you through how all of these pieces come together for getting a payload into memory. The first item in our chain is the artifact. And I feel like every other diagram starts out with me saying, the artifact is the executable or PowerShell script that runs our Cobalt Strike beacon payload. Right. But what the artifact does is it allocates memory for our beacon reflective DLL package. And this is assuming there's no stager, which we're going to assume for this diagram. But the artifact allocates memory for this package, and that memory could be RWX, that is in control of the artifact, and the artifact controls how much space it asks for. And it will copy our beacon reflective DLL package into that memory. Okay? When that's done, the artifact will call position 0 of the reflective DLL, which contains patched in code that will then call the reflective loader embedded in the reflective DLL. And whether this is done by jumping to a pointer or creating a thread is up to the artifact. But either way, this function called the reflective loader gets run. And what the reflective loader does is it walks backwards in memory to find the beginning of the reflective DLL package in memory. And this is an information gathering step to allow the reflective loader to allocate space for the beacon DLL in memory. And so this is very much the doing of our reflective loader package. So the reflective loader will request memory, and that memory has the permissions dictated by the reflective loader for our beacon DLL, and it will copy our beacon DLL into that space. Okay? And our reflective loader will then do something called going through the import table, where it starts loading any modules that our DLL will need and resolving function addresses. And as it resolves those addresses, it actually updates the import table of our beacon DLL in memory. And that's what's going on there. And when the reflective loader is done, it calls a function within our beacon DLL called the entry point. And it calls it by just jumping to it directly. So it just calls that entry point. It's not going to create a new thread to do this. And at this point, our beacon DLL is now running in memory. Okay? So I want to give you an idea of how some of the options I brought up in the last slide influence this particular process. And I really want you to appreciate that the aspects of the process being influenced are the steps taken by the reflective DLL package to load the beacon DLL in memory because it's easy to get confused by what's doing what. All right, let's go through these a little bit. So the first one that I want to talk about is use RWX. Use RWX influences the permissions right here, and that's going to be whether you have read, write, execute, or a combination of read, write, and read, execute, and that's what use RWX gives you. Of course, if module stomping is enabled, the initial permissions of this area of memory will be influenced by that, and module stomping changes this step from virtual alloc to loading a module and overwriting it, as I described earlier. So that's use RWX. The other one I brought up is image size x86 and x64. And what this influences is a value in the PE header that dictates how much space the reflective DLL will request for our beacon DLL. So if you want a bigger region, you can get that. And that's what image size x64 does. The other option is obfuscate. And obfuscate is a pretty neat option. Most of what obfuscate does actually takes place way back within Cobalt Strike itself when the reflective DLL is being built. And what obfuscate does is it actually takes parts that identified as a DLL but are optional and stomps them out. And so what you end up with is a bunch of random data here in the PE header, and the different section headers are all kind of stomped out a little bit as well. And the whole point of this step is just to make it a little bit harder to tell based on content that this is a reflective DLL. The other benefit of having obfuscate set to true, and it would be nice if I actually wrote obfuscate so you know what I was talking about. The other nice thing about having obfuscate set to true is that when your beacon DLL is loaded, it's loaded without the PE header. So it actually exists in the beginning of its memory space. So we'll put a 0 right there without the PE header. So that's another kind of thing obfuscate does. And as I come up with stuff, I keep adding it to obfuscate. So it's definitely an option that evolves over time. And so that's what obfuscate is giving you. Oh, the other thing obfuscate does as well is in that import address table, the libraries and function addresses are plainly visible, and obfuscate actually masks those so they're never visible except for the function being loaded one at a time. So again, that's just another content obfuscation trick. Another option that is very important, and I highly recommend you always set to true, is cleanup. And cleanup is a big deal. Let me explain why. What I'm showing you right here, steps 1, 2, and 3, is what is in memory when your beacon payload is being run, or your weaponized beacon payload. Now let's say that we're not actually using an artifact, but we're instead injecting beacon into another process. Well, if that's happening, if we're doing process injection, this artifact stuff is not there. And all we have is the reflective loader and the beacon DLL itself. Okay? And if you set cleanup to true, what beacon will do as soon as it runs is it will call free on the reflective DLL memory space. So it will free that content in memory and get rid of it. And so this evidence right here goes away. And now your process space has one less thing that can be used to look for you. And if you're doing process injection, you can see why this is attractive, because there's very little to point to your beacon DLL in that process context if you set cleanup to true. So that's the cleanup option, and it's pretty handy. The last one I'll speak to is sleep mask. Let me just kind of get rid of some of this. And sleep mask, what it does, find a good color, we'll just use yellow, why not? Sleep mask. What sleep mask does is when your beacon is about to go to sleep, sleep mask walks over all of the content of the beacon and applies Azure masking to it. So it'll do that to this whole space. And when your beacon is about to wake up, it will undo that masking of all the content inside of your beacon payload. And by that, the content of the beacon DLL itself. And this becomes a great way to obfuscate the content that indicates your beacon is there when it's not doing anything. So that's a little bit about how these in-memory evasion options interact with the chain of events that load your beacon payload into memory. I want to close out with a few thoughts on artifact tradecraft. I recommend that you avoid the use of RWX memory and threads which have a start address that is not associated with a memory mapped DLL or your executable itself. And by that, I mean modulus threads. Here's how I meet these goals in one of the artifact kit executables. I allocate memory that has read-write permissions, do my thing, and then flip it over to read execute when I'm done. For avoiding a modulus thread, in this case, I do have a need to create a thread. That's why I'm not just casting my allocated memory to a pointer and calling it, or to a function pointer and calling it. Instead, I create a thread, and I have it call a function inside of my executable called run, and that function takes its argument, which is the pointer to my beacon reflective DLL package, and casts that to a function pointer and calls it. And so that's just me taking care to avoid creating a thread that is not affiliated with a module on disk. Similar story when doing process injection. One way to avoid modulus threads when doing process injection is to create a thread that is suspended and has a desirable start address and get its context, update that context to have it call your desired start address of your payload next, and set that thread to this new context, and then resume it. And when you do that, the thread will have the desired start address, but will call your payload instead. One thing I did want to bring up related to the artifact kit is a little something about process injection. I very much recommend that you download the artifact kit and update patch.c, and if you need to, injector.c to get rid of rundle32. The artifact kit does migrate to rundle32 when it has to do process migration, and I'm absolutely certain you don't want that. I don't want that for you, but something has to be the default. It may as well be the worst default possible so that those who bother to follow my advice here benefit infinitely. This slide is a survey of the different artifacts in Cobalt Strike as of October 2019 and which characteristics they take on related to process migration, read, write, execute memory, or even creating a modulus thread. The big one I would be aware of here is the service executable, because if you use the psexec option in Cobalt Strike or the elevate service exe option, you will be using a service executable. Do note that the Cobalt Strike service executable migrates, and if you don't change the artifact kit, it will migrate to rundle32, and that's probably not what you want. Holy cow, we're at the end. In this lecture, I introduced you to weaponization, combining a payload with an artifact that will run it. I took you through different weaponization options to run the beacon payload, and we talked a lot about tradecraft. It's no longer enough to get an artifact past an endpoint security product. You have to think about the artifact's behavior, You have to think about your in-memory content and the process context you end up in, because all of these things influence whether or not you have code execution and a safe process context to do post-exploitation from. This concludes Part 4 of Red Team Operations with Cobalt Strike, Weaponization.